You have two conducting spheres connected by a metal rod. Okay, situation number one. I have a negatively charged balloon. I bring it near these two spheres. Bring it near, but I don't touch it. Okay? Bring it near. And then I take away the metal that's conducting, the metal rod in between the two of them. What can you conclude about the charge on the two spheres?
I got it.
Sydney, what's this?
Positive.
Why?
Because the electrons are going to run away through the little metal thing, and when you take it away, they can't come back.
So if this is negatively charged, the chihuahuas from here are going to go running over to here. So this is going to have excess chihuahuas, but you have St. Bernards left behind. The charges should be the same, okay, as long as you remove that. Situation number two, they're back to neutral. Situation number two, I bring the negatively charged balloon and I actually touch the first sphere.
Is the bridge there or not?
Bridge is still there. If I actually touch it and the sphere is there, then what's going to happen?
It's all negative.
It's all negative.
Yeah.
Why?
Because the charge disperses.
Beautiful. So if I actually touch it, then everything's going to be negatively charged because that negative charge is going to try and equalize everything out. Okay. Imagine that you have a number line. Q1 here, Q2 here. At this point right here, the electric field has a value of 0. Okay? Let's start with this. What are the units for electric field?
Newtons.
Newtons over coulombs. Okay? So the electric field is 0 right there. So what can you conclude about charge Q1 and charge Q2? Are they the same? Are they opposite? Which one is bigger?
They're the same.
Q1 is bigger and Q2 is smaller.
Let's establish this. Are they both going to have the same charge,
Yeah,
or are they going to have opposite charges?
Same charge.
same.
Everybody saw it on the same chart.
Yeah.
Why?
Because for it to be in
So
between the
they
two,
can, like,
it has
cancel.
to be the same charge. Or else, if one was different, then it would go to the.
They go in opposite directions.
So let's say that they're both positively charged. Okay? If both of these Q1 and Q2 are positively charged, right? If that positive test charge right there would feel what?
Repels back up.
Purple.
It would feel pushed by that one and it would feel pushed by
Q1.
that one. Okay? If these were both negatively charged, what would it feel?
Hold back.
Pulled and pulled. If this was positive and that was negative,
It'd be
there's no way the electric field can be 0 in between, because it's always going to be pushed and pulled by one of them. Okay? So in between, the only way that you can have a net electric field of 0 is if
They were both one charge.
yes. Okay. So we know that they're both the same charge. I don't know if positive, negative doesn't make any difference. But which one has to be the bigger amount of charge? Q1 or Q2? Q1. Why?
Further away.
Farther away.
Because how do you calculate the value of an electric field?
KQ over
KQ over
R squared.
R squared. Okay? So therefore, since this field here is a greater distance, that's the only way that can balance that out. Okay? Right? So that Q here, that Q1 has to be bigger or smaller? Bigger because it has a greater distance. Next problem, I promise you, will be there.
Two plates? Two plates? 225?
It's not 12. What? This will say 12 centimeters.
Yes, 12 centimeters.
Two plates, I think that's 225, right?
Okay. So imagine this. You shoot an electron in between a positively and negatively charged plate. The electron is moving at 5.8 times 10 to the 7th meters per second.
Yeah.
The electric field is 1.8 times 10 to the 4th meters per coulomb. I want to know how far is this thing going to get deflected and in which direction. Start with this idea. What's the direction of the electric field in between the plates? Up or down?
Yeah.
Why is the electric field pointing up?
Positive test charge.
Positive test charge would get pushed and pulled.
Yeah.
So the direction of the electric field is pointing up.
Yeah.
Okay?
Yeah, buddy.
Got that?
Yes, sir.
So, you know the value of the electric field. You know it's an electron.
Force.
You can find Beck. Right? So, you know the value of the electric field. And since it's an electron, the charge is 1.60 times 10 to the negative 19 coulombs. So you can find the value of the force. Once you know the value of the force in your word, we can find the acceleration. Right?
That equation.
So then I can take that force and divide it by the mass to get
Acceleration.
an acceleration. Going to be a pretty big number.
Really big?
Okay? Pretty big number. Okay. I'm just trying to get you through the process. Okay? Now, this is like a lemming problem. What happens in the X?
Stays in.
What happens in the Y?
Stays in the Y.
So even though there's an electric field, are there any forces acting in the horizontal direction? No.
Never.
So just like when you shoot something off of a cliff, what do you assume about the horizontal velocity? So this is basically a lemming problem on steroids. Okay? It's a lemming in an electric field.
Didn't we do this?
Yes, and now you know why.
Okay.
So you got 5.8 times 10 to the 7th meters per second. You know that it travels a horizontal distance of 12 centimeters, right? So what are you going to do with 12 centimeters? So this is going to be 0.12 meters. How are you going to figure out how long it's traveling?
Where the electron starts going down.
You're going to take that and divide that by that velocity of 5.8.
Basically the same thing, but the now.
Okay? Because we're assuming that the horizontal velocity remains the same. Just like any lemming problem, the horizontal velocity remains the same. So this is going to get us some value of time, which is going to be a really small number. Okay? Because it's not traveling very far and it's going almost the speed of light. So then you're going to know an acceleration and then you're going to know a time. So how are you going to find out the deflection? Which would be similar to me asking you, hey, I dropped the baseball, how far does it fall? What are you going to use? Not that equation.
Is it the one?
Oh! X equals 1/2 AT squared plus V naught time. But what happens in the X stays in the
X. No.
So what's your V naught velocity in the vertical direction? 0. So you're gonna know that acceleration, and you're gonna know that time.
Oh, you can
Okay.
figure out it.
That's an X, by the way, or distance. Okay? So this is just nothing but me throwing this baseball. You have the range, how far the baseball goes. You know the acceleration due to gravity. If you know how long it's in the air, you can figure out how far it falls. This is nothing but a lemming problem. Okay? That's all it is. It's just a lemming problem. I promise you, you're going to have something like that. Real quick, one other problem that you might consider is that you have a 1 kilogram mass over here, charged to 10 microcoulombs. You have a 2 kilogram mass over here, charged to 8 nanocoulombs or microcoulombs, and it's separated by a distance of 50 meters, whatever that is. And you need to find the net force in between the two objects. So what two considerations do you have?
Gravity,
Gravity going old school F equals,
big G, M1, M2 over R.
that is only attractive. They're both positively charged. Okay. The difference between those two is your net force. Okay. I know the south of you've got to go. I will email you out the solutions to this. It's just a couple of simple problems,
Wednesday.
but something to consider.
Or it might be on the test.
That might be a little difficult.
I don't know. Can you pass me